In this video, we're going to be going over what a breadth first search is. So a BFS tree is a tree you get when you run a breadth first search on a graph from a chosen node. It shows the order the nodes are discovered, the shortest path structure, in an unweighted graph. And it shows the parent-child relationships, formed during the BFS. So why is it called breadth first search? It gets this part of its name because it expands outward horizontally before getting deeper. So, for example, when you drop a pebble in water, the ripples, they're going to expand outwards like a circle, not straight down. So let's consider an example. So we have a tree like this. Let's start our BFS here. So at A, what is our queue going to look like? And what will we have visited? So our queue is going to have A, and we're going to have visited A. Now after this, we have to visit the neighbors. So we have B and C. So we're going to visit in our queue and our visited. Let's actually change how this is set up. So your queue is going to be B, C. And we're going to have A, B, C. So in your BFS tree, it's going to be A maps to B and A maps to C. Now after this, so this was for your root. Now we're going to visit B. So we have to look at the neighbors of B. So at B, this was the neighbors of A. At B, you're going to have neighbors of D and E. So your queue is going to be C, D, E. And you're going to have visited A, B, C, D, E. And then your BFS tree, you're going to have B pointing to D and B pointing to E. Now we're going to visit C. So at C, we're going to have a neighbor of F. Here we had a neighbor of D and E. But here, when we are visiting C, our Q is going to be D, E, F. And we're going to have visited A, B, C, D, E, F. Now in your BFS tree, you're going to have C pointing to F. Now after this, we're going to visit D. So at D, we have no new neighbors. So your Q is going to be E, F. And then we're going to visit C, or E. So your neighbor is going to be G, and your Q is going to be F, G. Now we're going to have visited A, B, C, D, E, F, G. And in your BFS tree, we're going to map this as a connection of E pointing to G. Now we're going to visit F. So F has no new neighbors. So we're done here. Now our final tree is this. So what we can see is our final tree will look exactly the same original graph, but this is a coincidence. Because a BFS tree, it only contains the following. So we only have the edges that we used when discovering the nodes. So if the graph had extra edges, they wouldn't appear in the BFS. So let's go back to our definition of a BFS tree. The conditions are that 1, it has to be a tree. No cycles. Even if your original tree had graphs. Actually, move this out the way. And it also has to show your shortest path. So in an unweighted graph, your BFS is going to ensure that the path from the root to any node in the BFS is the shortest possible path. Which means that it has the fewest edges. Thirdly, it has to have edges. So your level is your distance from your start node. Like we can see here, A is level 0, 1, 2, 3. So it has to have that level structure. You might have heard of depth first trees and BFS trees. They're different because the BFS, you're going to use Q. It's, again, like we said, level by level. It's shortest path. That's unweighted. And it has a wide expansion. Now, on the other hand, a DFS is going to use stack and recursions, it goes deep instead of horizontal. So we'll say deep expansion. And it's not guaranteed that it would be the shortest path. So here we can see our code snippet for how we would code a basic BFS. So we have Q node, Q is equal to new linked list, and generic type set node visited equal to new hash set, q.add start, visited.add start, while the queue is empty. Well, not the queue is empty. Node current is equal to q.remove for node neighbor current.neighbor if q.contains neighbor visited.add neighbor q.add. This edge is going to become part of the BFS tree. So we have here neighbor.parent is equal to current. So neighbor.current, this is how our BFS is formed. What we see is BFS, it doesn't follow a branch fully, so we're going to use recursion. Or sorry, it does not use recursion naturally. No natural recursion, and it requires a queue. Very important, needs a queue to work. It doesn't go down one branch. So we have no cycles, add that to this list, shortest path, and level structure.